Welcome to the second video lecture on transformers. In the previous video lecture, I introduced what is a transformer and what are the main components in the transformer. So there I said that the transformer will have two main components, magnetic core and the windings. So the core is going to provide a path for the magnetic flux to flow, and the voltage source is coupled to the one winding and load is coupled to the other winding. In this video lecture, we will look at ideal transformer. In an ideal transformer, you won't find any losses. If you provide X amount of input power, you will get the same amount of power from the output. But when it comes to the practical cases, you won't be able to find an ideal transformer. So what we are going to do in a transformer is that we are going to connect a voltage source to the primary winding. So when you couple the voltage source to the primary winding, what would happen is the flux is going to produced in the core. So how this flux is going to produce is by means of the magnetization current. So this magnetization current is going to be lagging the supply voltage by 90 degrees. So you provide you connect the voltage source, and thereby a current is going to flow and it is going to produce the flux inside the machine. So we usually connect a sinusoidal supply to the primary, therefore the flux inside the core would vary in sinusoidal manner. When the load is disconnected initially, primary current or the supply current would be equals to the magnetization current. Now when you have a flux flowing through the core, due to the varying flux, there will be a voltage induced in the primary as well as in the secondary. And this voltage induced in the primary would depend on the number of turns in the primary winding, and the voltage induced in the secondary would depend on the number of turns in the secondary winding. So the induced voltage in the primary would be NP times d phi over dt. Induced voltage in the secondary is Ns times d phi over dt. So you can find a ratio for the induced voltage in the primary to induced voltage into the secondary winding, which is going to be equals to Np over Ns. So Np over Ns is known as the turns ratio of the transformer. So this induced voltage would be sinusoidal because you have a sinusoidal flux variation. So you could find out the RMS voltage of the induced voltage. That can be represented by 4.44 times N times F times phi m. Here N is the number of turns of the winding, F is the supply frequency, and phi m is the peak flux flowing through the core. So depending on the primary winding turns, you will have one voltage. Depending on the secondary winding secondary turns, you will have a different voltage in the secondary terminal. So as I said, when a voltage is applied to the primary winding, a current is going to flow. So that current would be lagging the voltage Vp by 90 degrees, and that will produce the flux inside the machine or the transformer. So now due to this flux, there will be a voltage induced in the primary, which would be in the same direction of Vp. Then there will be a voltage in the secondary. So depending on the way how we are going to wind the secondary of the transformer, the direction of secondary voltage would differ. Normally, the direction of voltage of the primary and secondary would be in phase. But if we have if that is the case, and if we try to represent in the same phase diagram, in the it should E2 should be in the same direction, but that would make the visualization difficult. Therefore we draw the E2 phasor 180 degrees from the VP or E1. So E2 and secondary voltage would be in the same direction. Now if we connect a load to the secondary, since you have a voltage, there would be a finite current flowing through the secondary winding. So now there is a secondary current. So due to this secondary current, the flux inside the mesh transformer is going to be disturbed. Initially you had a phi amount of flux, but now due to Is there would be additional flux generated in the core. So that is going to disturb the operation of the core. So what would happen is, now there would be a current flowing through the primary winding to negate the flux generated by the secondary winding. So now the primary current would have two components. One is the magnetization current, which is going to set the flux inside the machine, and that is the IMT, and there would be another component of current which is going to negate the effect of flux produced by the secondary current, which is the IP1T. Therefore the total current of the primary is the addition of IP1 plus IMT. Now we can represent this effect using the phasor diagram. So if we connect a lagging load to the secondary terminal, so you have Is which is going to lag the E2. Now due to this Is, there would be a current in the primary which you have in the same direction, IP1. So here, due to representation, you have in the opposite direction, but they should be in the same direction. So IP1, then you have the IM. So the addition of IP1 and IM is the current drawn from the supply. So these are the important relationships. Turns ratio is defined as the number of turns in the primary to number of turns in the secondary winding. Usually turns ratio is denoted by simple n. Then the voltage relationships. Primary voltage to the secondary voltage ratio is equals to number of turns in the primary winding to number of turns in the secondary winding. That means the voltage ratio to the primary voltage ratio of primary to secondary is equals to turns ratio. So instead of using the scalar quantities, you can use the phasor notations. Then Vp over Vs is equals to Vp angle theta p over Vs angle theta s, and it is going to equals to number of the turns ratio. Then in ideal transformer, output power is going to be equals to the input power. So the input power is IP times Vp, output power is Is times Vst. Therefore primary current to secondary current ratio is equals to Ns over Np, which is equals to 1 over turns ratio. Again, the currents can be represented in phasor notations. Ip over Is is equals to Ip angle theta p, Is angle theta s, which is equals to 1 over n. Now we can write the equations for the active, reactive and apparent power. In case of active power, input active power is Vp Ip cos theta p, output active power is Vs Is cos theta s. for ideal transformer, input power is equals to output power. Therefore, the primary angle difference between the primary voltage and primary current would be equals to the angle difference of the secondary voltage and current. Reactive power is given by QP Vp Ip sin theta p, which is going to be equals to Vs Is cos theta s, which is the secondary reactive power. In case of the apparent power, primary apparent power is Vp Ip, which is going to be equals to Vs Is, the secondary apparent power. Now we will move on to the dot convention. The reason to use dot convention is to find out the direction of voltage and current flow. So in a transformer, in the simple one, you have two windings. So each winding will have two ends. In one end you could find this dot. So if you want to find out the correct direction of voltages and current, the dot should be available in both windings. Now we will see how we can find out the voltage polarity. Now if the primary voltage is positive in the dotted end with respect to the undotted end, then in the secondary side also, secondary winding also, the voltage at the dotted end would be positive with respect to the undotted end. If it is in the other way around, that is the voltage is positive in the undotted end with respect to the dot end in the primary, in the secondary winding, undotted end voltage would be positive with respect to the undotted end. Then we will see how the current direction can be found out. If the primary current is flowing into the dot, then the secondary current is flowing out of the dot. If the primary current is leaving the dot, then the current in the secondary is moving into the dot. So with this method, this dot convention, you could find out the voltage direction as well as the current directions. Now I will move on to the third section of this video lecture, which is the impedance transferring. In case of the transformer, we are going to connect the load to the secondary winding. So now the impedance seen from the secondary side would be ZL. But what would be the impedance which you would see from the primary side? So that is what we are going to find out with this impedance transferring. So here the impedance in the secondary side is ZL, secondary current is Is, and the voltage is Vs. Primary voltage is Vp and the current is Ip. Number of turns in the primary is Np, number of turns in the secondary is Ns. So I have marked the impedance which you see from the primary winding as ZL dash. First we can write an equation for the load seen from the secondary winding. So ZL would be equals to the voltage of the secondary winding divided by the secondary current. Then the load seen by the primary winding is ZL dash equals Vp over Ip. Now using the voltage relationships, I can write Vp is equals to N times Vs. Using the current relationship, I can write Is is equals to N times Ip. So I will consider this ZL dash, which would be equals to Vp over Ip. Now Vp is equals to N times Vs. Ip is equals to Is over N. So when I simplify this part, I would get N squared times Vs over Is. So if we refer the load seen by the secondary side, ZL is equals to Vs over Is. Therefore, ZL dash is equals to N squared over ZL. So this is the impedance transferring relationship of a transformer. So with that, I will conclude the second video lecture of transformers. In this video lecture, we looked at the ideal transformer, what are the relationships, Phasor diagrams of the ideal transformer. Then we looked at the dot convention, which is used to find the direction of the voltages and the currents in the primary and secondary winding. Finally, we looked at the impedance transferring of a transformer from primary to secondary and secondary to primary. So these are the reference that I used for this lecture. Thank you.